Good afternoon, everyone. My name is Wu Man. I come from Hubei University, one of the most beautiful universities in China. Today, we will talk about combining data filter and data sampling for cross-company defect prediction, an Empricial study. This is a joint work with Yu Xiao, Zhang Yan, and Fu Mandi. First of all, let's talk about the motivation about our work. Software defect prediction is one of the most important software quality assurance techniques. It aims to detect the defectfulness of new software module while learning from defect data. So far, many efficient software defect prediction approaches have been proposed, but they are usually confined to within-company defect prediction (WCDP). WCDP works well if sufficient data is available to train a defect prediction model. However, it is difficult for a new company to perform WCDP if there is limited historical data. Cross-company defect prediction (CCDP) is a practical approach to solve the problem. It trains a prediction model by exploiting cross-company CC data and then applies the model to within-company (WC). Then, we will talk about the existing approaches about the CCDP. Now, I want to talk about something about defect prediction. The first one is to apply the data filtering method to find the best suitable training data. The second mainstream way is to design effective defect predictor based on transform learning techniques. The third mainstream way is to apply unsupervised classifier that doesn't require any training data to perform CCDP. Therefore, the distribution gap between the training project data and the target project data is no longer an issue. There are three kinds of data sampling. First one is data level methods. Second one is algorithm level methods. And the last one is ensemble learning. However, there are some problems. The one problem is to find what extent combined data filter and data sampling can contribute to CCDP. Another problem is how to make better use of them to improve CCDP. So, I will begin to introduce our approach. Due to it is still unclear what extent combined data filter and data sampling can contribute to CCDP, and how to make better use of them to improve CCDP. Our paper proposes an approach in which data sampling is combined with data filter to cope with both class imbalance problem and the influence of irrelevant CC data. The NN filter was proposed by Qiu Han. Based on the widely used KNN algorithm, NN filter can find out the most similar K multiplied by N instances from CC data, where N is the number of WC instances and K is the parameter of the KNN algorithm. The DB-scan filter was proposed by Kawa. It assumes that the CC instances which are in the same cluster as WC instance are the most valuable instances in CC data. SMOTE was proposed in 2002. It is an oversampling approach in which the minority class is oversampled by creating synthetic examples. Here is the procedure of SMOTE. Random undersampling is a simple method to select a subset of non-defective instances randomly, and then combine them with defective-prone instances as a training set. The procedure of random undersampling is as follows. The primary goal of this study is to evaluate the data pre-processing technique in which data filter is combined with data sampling. 8 different scenarios would be produced depending on whether data filter is performed before or after data sampling. Okay, then I will detail our experiments. In this experiment, we employ 15 available and commonly used datasets, which can be obtained from premise. These 15 datasets have the same 20 attributes, so we can apply all attributes information directly. This table shows the details about the datasets. In the experiment, we employ 3 commonly used performance measures, including PD, PF, and G-measure. We try to find answers to 2 research questions. The first question is which approach we proposed is the most efficient compared to other approaches for CCDP. From the picture, we can see that in terms of the defect detection rate, approach 1 outperforms other approaches for NB model, which shows its effectiveness in finding defects. However, approach 1 has a little high PF value. In terms of the false alarm rate, although approach 3 is the best, it performs not well in PD, which makes it hard useful in practice. From this picture, we can find that although approach 8 appears to be better at PD than other approaches for RF model, it performs the worst in PF. Approach 1 presents generally higher PD and lower PF than other approaches for RF model. From the last picture, we can see that approach 8 shows better PD than other approaches for LR model, but its advantage is rather limited. Approach 1 presents generally higher PD and lower PF than other approaches for RF model. Now we can gain the following results from some tables. In Table 1, on more than half projects, approach 6 performs better than the other 7 approaches for NB model. However, approach 1 achieves the best average G-measure value for NB model. In Table 2, on 9 projects, approach 1 achieves higher G-measure than the other 7 approaches for RF model. In addition, approach 1 achieves the best average G-measure value for RF model. In Table 3, on 6 projects, approach 1 achieves higher G-measure than the other 7 approaches for LR model, which approach 8 displayed similar or slightly worse performance than approach 1. In addition, approach 1 achieves the best average G-measure value for LR model. So we can answer the question. We can conclude that NN filter performed prior to RUS approach 1 has significantly better performance than the other 7 approaches. In this section, we discuss several validity threats that may have an impact on the results of our studies. The first one is external validity. Although these datasets we performed have been widely used in many software defect prediction studies, we still can claim that our conclusions can be generalized to other software projects. Nevertheless, this work provides a detailed experimental description, including parameter settings, thus other researchers can easily replicate this Empricial study on new datasets. The second one is internal validity. In this work, we only use three classifiers: naive, hidden forest, and logistic regression, due to its popularity in defect prediction. In addition, we choose two representative data filtering methods, N-filter and dbScan filter, two representative data sampling methods, RUS and SMOTE. The third one is constructor validity. In our experiments, we mainly use PD, PF, G-measure to measure the effectiveness of the 8 approaches. Nonetheless, other evaluation measures such as AUC measure can also be considered. Finally, we give our conclusions and talk about the future work. In this paper, we propose data filter combined with data sampling to overcome the influence of large irrelevant CC data and class imbalance problems that often affect CCDP models. 8 combination approaches are investigated. We conduct experiments on the 15 datasets to evaluate the performance of the proposed 8 approaches, and found that N-filter performed prior to RUS approach 1 had significantly better performance than the other 7 approaches. In the future, we would like to employ more datasets to validate the generalization of the derived conclusions. Thank you for your listening. That's all.